Hey guys, today we are going to study about motion in a straight line. Before going into the topic, we will just see all of the synopsis that we are going to study in this concept. First, we will be discussing about rest and motion. Next, we will be discussing about what is the difference between distance and displacement, and a lot of terms like average speed, instantaneous speed, average velocity, instant velocity, motion in a straight line, motion with constant acceleration, freely falling objects. So, first, let us discuss about rest and motion. What is called as rest and what is called as motion? A body is said to be at rest when its position does not change with respect to time. That is, with respect to time, if a body is at a stationary position without moving, it is said to be at rest. And a body is said to be in motion when its position changes with respect to time. That is, its position is different at different time. Coming on to distance and displacement. Suppose a particle is at A at time t1 and at B at time t2 with respect to the frame. During this time t1 to t2, the particle moves along the path ACB. The length ACB is called the distance traveled by the particle in t1 to t2. The shortest distance between the initial and final point AB is called the displacement. So, that is, actual path traveled by the particle is called the distance, and the shortest distance between initial and final point is called the displacement. One more thing to be noted is, distance may sometimes be equal to displacement also, but displacement can never be greater than distance because displacement is the shortest distance between initial and final point. So, displacement will never be greater than distance. Now, average and instantaneous speed. The average speed of a particle is defined as the total distance traveled divided by the total time interval. So, V average is equal to distance divided by time. As delta t approaches 0, delta s also approaches to 0, but the ratio delta s by delta t is a finite limit. The instantaneous speed at a time t is defined as limit delta t tends to 0, delta s by delta t. The average speed is defined for a time interval and instantaneous speed is defined only at a particular instant. Now, average and instantaneous velocity. The average speed of a particle is defined as the displacement divided by the total time interval. There we saw average speed is equal to distance divided by time. Here, average velocity is equal to displacement divided by time. Here, we will be dealing with only the position vectors, initial and final position vectors. Now, the instantaneous velocity at a time t is defined as limit delta t tends to 0 modulus of delta r vector divided by delta t, which is delta s divided by delta t. Note that the instantaneous velocity and instantaneous speed is the same because in a small time interval, both the distance and displacement is the same. Now, motion in a straight line. When a particle is constrained to move on a straight line, the description becomes fairly simple. We choose the line as the x-axis and the suitable time instant as t equal to 0. Generally, the origin is taken at the point where the particle is situated at t equal to 0. The position of the particle at time t is given by its coordinate x at that time. The velocity v equal to dx by dt. The acceleration a equal to dv by dt, which comes out to be d square x by dt square, because v equal to dx by dt. Now, moving of motion of a particle with constant acceleration. Let us consider the acceleration of a particle is a and remains constant. Let the velocity at time 0 be u and the velocity at time t be v. Thus, we have the acceleration is constant because since the acceleration is constant, we can write this equation dv by dt equal to a, which is dv equal to a dt. As time changes from 0 to t, the velocity changes from u to v. So the left hand side of the summation is made over v from u to v, whereas on the right hand side the summation is made on time from 0 to t. Evaluating the integrals, we get v minus u equal to at, that is v equal to u plus at. This is one equation of a equation of particle moving in constant acceleration. Now v can also be written as dx by dt. So dx by dt is equal to u plus at. Dx equal to u plus at into dt. At t equal to 0, the particle is at x equal to 0. As time changes from 0 to t, the position changes from 0 to x. So on the left hand side, the summation is made on position from 0 to x, whereas on the right hand side, the summation is made on time from 0 to t. Evaluating the integrals, the above equation becomes x equal to ut plus half at square. From equation 3.12, b square equal to u plus at whole square. U plus at whole square can be written as u square plus 2uat plus a square t square. Now with this, in these two terms, we can take 2a common and you can write ut plus half at square, which is x. So b square equal to u square plus 2ax. This is another equation. The three equations are collected below in the table. They are very useful in solving the problems of motion in a straight line with constant acceleration. Now we will see the distance travelled in the nth second. Now how we will find this is, like, we will be just simply subtracting the distance travelled till the nth second minus distance travelled during the n minus 1 second, which gives us the distance travelled only in the nth second. So the derivation is given here. Sn equal to un plus half an square, which is the distance travelled in from 0 to n seconds, and Sn minus 1, which is the distance travelled from 0 to n minus 1 seconds. Now simply subtracting these two will give us the distance travelled during the nth second. So doing the calculation, we get distance travelled during nth second equal to u plus a by 2 into 2t minus 1. Now freely falling objects. A common example of motion in a straight line with constant acceleration is free fall of a body near the earth's surface. If air resistance is neglected and the body is dropped near the surface of the earth, it falls along a vertical straight line. The acceleration is in the vertical downward direction and its magnitude is almost constant if the height is small as compared to the radius of the earth. The magnitude is approximately 9.8 meter per second or 32 feet per second, but generally will take us 10 meter per second square for our convenience. If we take vertically upward as a positive y-axis, the acceleration is along the negative y-axis, and we write a equal to minus g. So the equations in the previous table becomes v equal to u minus gt, y equal to ut minus half gt square, v square equal to u square minus 2gy. So let us see this problem. A ball is thrown up at a speed of 4 meter per second. Find the maximum height reached by the ball. Take g equal to 10 meter per second square. Now we have this equation v square equal to u square plus 2ay. In this, we will consider upward motion as positive, so the acceleration is downwards, which is minus 10. So we know at the point of maximum height, the final velocity will be 0. The ball will be coming downwards. So final velocity will be 0. Initial velocity, which is given 4 meter per second, and the acceleration we know at that is minus 10. So 0 equal to 4 meter per second whole square plus 2 into minus 10 meter per second square into y. So solving this, we get y equal to 0.8 meters, which is the maximum height reached by the ball.